I will give 4 talks on singular supports in equal and mixed characteristic. So yeah, so let me explain rough plan. So in geometric case, so in this case, it's a smooth scheme of a field. Then so this is due to Beilinson, and the theory there is well established. But in mixed characteristic case, so in this case, so I made some attempt, but the theory is far from complete. So probably in the first 2 lectures, I recall Beilinson's theory. Then I shift to this second subject in the later lectures.
So initially, Beilinson proved it's a singular support next then, but you also proved, I mean, at the same time. I think you, it's around 2015 or so. But anyway, for defining the singular, the characteristic cycles, it is in
yeah. So this time I will not talk on character cycles. This time I will concentrate only on singular support. Okay. Okay, so let me fix notation. So so I start with this geometric case. So K will be a field. So X smooth scheme over K. Then we have this cotangent bundle. So this is a vector bundle over X associated to the sheaf of omega 1. So we assume X is smooth, so this omega 1 is locally free. So we have associated vector bundle, which is the definition of the cotangent bundle. So this is the geometric stage we will work on. And we consider sheaves. So lambda will be finite field. Finite extension of FL. So L is different from characteristic of K. Then okay, so we consider object of DBC of the eternal site of X. So in many cases, we don't need this constructibility, but but I don't care so much about the general case. So mostly we work on constructible complexes. And following Beilinson terminology, we call sheaf equal object of this DBC. Okay, so we are interested in sheaf of this category, and singular support is subset of this cotangent bundle.
So the fact that lambda is finite, it is not very. Is it ever used that lambda is finite? It could be an infinite extension of FL even though.
Yeah. This is just for simplicity.
But it is never, almost never. I mean, I suppose it's not used because I'm not sure. Actually, the simple object don't change between FL bar and other. But still.
Yeah. Sometimes it's convenient to work with FL bar. Yes. Yeah. Okay. Yeah. So conical close. So C. So this C is a closed subset of vector bundle. Is called conical if C is stable under GM maximum. So this is a vector bundle, so it carries natural GM action, multiplicative group, and singular support will be a closed conical subset. So conical means that this C is stable under this GM action. Okay, so singular support of F will be such C, closed conical subset. So the first goal of this lecture is to define this singular support. So this singular support is a closed conical subset defined by this F, but this relation is not so direct. So the definition format for so this is just a general format, so it will be vague. So it goes like this. So first we define the notion of micro support. So we say F is micro supported on C if a certain functorial property on C implies the corresponding property for F. So we want to define what is the singular support, but to define this, first we define the notion that F is micro supported on C, and so here this is stated in a vague way. So this depends on the context, actual context. So I will make this precise shortly in the original Beilinson's case, and later I will modify these properties to be adjusted in a mixed characteristic situation. So in any case, we consider certain property C and certain property on F, and if we have such implication, then we say that F is micro supported on C. Then, so this is the first step in the definition, and once this is defined, then we can make a definition. If the smallest C on which F is micro supported on C. So usually if C is larger, then yeah.
And if C is everything, then it's satisfied.
I'm sorry?
If C is the full cotangent bundle, then, then the condition is verified.
Yeah. Yeah. C is yes. So if we have two C and C prime, and if F is micro-supported on C, then F is also micro-supported on the larger one. but we so we say that if there's such smallest one, then we define singular support to be the smallest C. So the definition goes along with this format. But so as I said, if F is micro-supported on C, and C is a subset of C prime, then F is micro-supported on C prime. So we usually have this implication, but the problem is that problem is the following. So suppose F is micro-supported on C and another closed conical subset on C prime. Then we expect that F is micro-supported on the intersection. But this is a non-trivial thing. So if we have such implication, then the existence of the smallest one will be easily proved. But this implication is non-trivial, so we don't know a priori the existence of singular support. So we have to prove something.
And even if it exists, then formally the restriction to open, which certainly should hold, is not clear. That it, suppose on a risky open it is micro-supported on some C, then it should on the full thing be micro-supported on the closure of this.
No, it's not. So you have to enlarge a little bit on the boundary.
No. It is micro-supported on something which restricts to C on the. No, I didn't say it right. It should be micro-supported on something which restricts to the thing on the open. But this is not. Yeah. So
It's not enough.
it's not.
Okay, so far any question? Okay, so so as I said, the existence is non-trivial problem, but Beilinson proved the existence. So by reduction to the projective space. So I will briefly tell you what is the advantage of working on this projective space. So we want to define certain closed conical subset. So closed conical subset C is determined by its base. So base is called B, is the intersection with the zero section. So C is called subset of the vector bundle. So you can take intersection with the zero section. Then you get the closed subset of X. So this is one thing. And another is the projective relation. P of C. So this is the closed subset of projective divided. Okay, let me specialize this cotangent bundle case. So closed conical subset is determined by its intersection with the zero section and its projectivization. And for singular support, this base is given by the support of the sheaf. So this part is easily determined. So the real problem is to determine the projectivization. And if X is the projective space, we can use the Radon transform. So we have projective space. Then we have the universal family of hyperplanes. So Pn, the dual projective space. So this is the modular space of hyperplanes. So we have a universal family of hyperplanes. So we have natural projections like this. And so Beilinson uses the Radon transform. So this is a naive Radon transform. So usually, if you define Radon transform, you put this, some twist and shift. But this is a naive one, so I ignore this kind of thing. So this is simply, so first you pull back by this projection and then push it down to by the other projection. So as usual, I omit the R to denote the derived factor. So this is the Radon transform. So he uses this construction, and so I defined this Q as a universal family of hyperplanes, but we have natural identification. So this universal family is the projectivization of the cotangent boundary here. So we want to capture the projectivization with a singular support. So, but this will be closed subset of this projectivization. So Beilinson captured this subset by using this construction geometrically. So this I will explain in the first part of the course.
May I ask a question?
Yes.
Is it possible, instead of reducing to Pn and using the Radon transform, to reduce to An and use the homogeneous Fourier transform?
I didn't try, so yeah, I don't know. Okay. Any other question? Okay, so now let me go. Yeah, the first task is to make this format precisely. Yeah, the first task is to make this so I will give precise definition of this property and the corresponding property. Okay, now let me go start. Okay, let me start with this side. So this side is given by the local acyclicity. So let me start with recalling the definition of local acyclicity. So F, they are most schemes. And FB a sheaf on X. So in the sense here, so I take prime number invertible on the schemes, and this is the object of DBC. Okay, then we say F is so this yeah, both are F. So this most means F acyclic, or in more classical terminology, if small f is locally acyclic relatively to F, but it's long, so it's we just go like this. If the following so we consider specialization of geometric point. So T and S are the geometric points on this target. So geometric specialization means that we consider structural localization. Then so of course we have closed point, and the specialization is almost from T to this structural localization. Then we can consider so because this map is given, so we can consider this Cartesian diagram. And let me call I and J, closed fiber and generic fiber. Then we have a conical motion. So we have put back of our sheaf on this space, and also that space. And there is a conical motion between these two by after taking this operation. And the condition is that this is the isomerism.
you say geometric point, in some reference it's spec of a algebraically closed field going to the scheme, in some cases separably closed, but here it should be the separable closure of
separable closure, yes.
the residue field in order to the fiber will be right. So it isn't, well, it depends on the...
Yes, thank you, yes. So for me it's a separable closure. So this is the definition of local acyclicity. So this can be described by
I'm not parsing the definition. So fxt lives on which scheme?
fxt is there.
Yeah.
And so you can take direct. Sorry. Yeah. Thank you.
Okay.
Yeah. Thank you. Okay.
You are not assuming that f is killed by some integer.
Sorry?
You are not assuming that f is killed by some integer imparting on y?
すみません、聞こえない。Sorry, I have a problem.
All his sheaves are coefficients in some field of characteristic different from P.
Okay.
From the beginning.
I see. So in that case, this taking algebraic closure and separable closure, does it make difference?
I don't think so. So there should be no difference in that case. Okay, so so there's a little more one more terminology. So we say f is universally f acyclic if for every monstrum the base change is let's say G prime star F acyclic. So there is this ULA, universally locally acyclic, but so it's defined in this way. So so this is the end of definition. So that this condition is stroke-wise it says the following. So this isomorphism this isomorphism means that for every geometric point this morphism this morphism is isomorphism. So this small x is above S. So we have natural morphism from the structural localization to between structural localizations, and we can take geometric fiber at this specialization. So, and the isomorphism there means that stroke-wise we have this isomorphism. and this is called the Milnor fiber. Yeah. So in the classical case, the mapping cone, this morphism is a vanishing cycle. So the local acyclicity means that there is no vanishing cycle in the classical case. And yeah, okay. Okay, so let me give some examples of this such local acyclicity. The first case is if f is smooth and if sheaf is locally constant. Then f is f acyclic. So here locally constant means that for every degree the cohomology sheaf is locally constant. So this is the local acyclicity of smooth morphism. So this is the classical thing in SJ4. Okay, and the second case is if the target is spec of K and if it is finite type, then for any f, f is f acyclic. So this is generic, special case of generic local acyclicity. In SJ 4.5.
But here it is trivial essentially. If you just over a field, there is nothing to prove.
But maybe you want to say universally, locally.
Maybe universal.
Yeah. Yes. Yes, yeah, you're right, yeah. So the next case is a generalization of the first one. So if the first morphism is f acyclic, and if the second morphism is smooth, then the composition is f acyclic. So this is the generalization of the first one. So this is in SJ 4.5 by Luke look easy. And the next one is characterization of local equivalence constant sheaf. So let's take F to be the identity. Then this is F acyclic. If and only if F is locally constant. And the last one is consequence of proper Beilinson theorem. So if F is proper, and the composition is F acyclic, then the direct image, then the second one, then second one is F star F acyclic. So this is the consequence of proper Beilinson theorem. Okay, so this is the review of local acyclicity. So far, any questions? Okay, then let me continue. So I give I state a definition. So this was one point. So I'm not really, so I just defined the property for F. So property for C is not yet defined, so I cannot make a precise definition here, but let me write the definition first, and then I will define the remaining terminologies. Okay, so X smooth over K, and F C from X, and C is closed conical subset. So I want to define what it means. So F is micro supported on C. So I want to define what this means. So we say F is micro supported C if the following is satisfied. So I erased already here, but it should mean that certain property on C should imply certain this local acyclicity. So it goes like this. So let H. So Beilinson considered two morphisms. So one is going to X, and he needs one more morphism. Be morphisms of smooth schemes over. Okay. So he considered two morphisms. So one is going to X, and the second is from this W to another scheme Y. Then if the first one is C transversal, so I need to explain what this means. And the second one, and if the second one is H0C acyclic, then this second one is H-stiff acyclic. So I also need to define what this means. So this is the property for F. So this property for C should imply this property on F. So this is the Beilinson's definition. Okay. Yeah, before making this precise, so here I just said this is the second one is just acyclic, but we can say, so this is equivalent to say that we can also put universally. So it's equivalent. It will be equivalent. And if you read Beilinson's original paper, this second terminology is also written transversal in Beilinson. So these are two different notions, but he used only one terminology. So it was fairly confusing, so I changed the terminology. Mm-hmm. Mm-hmm. Okay. Okay. So I'm going to define this transversality and acyclicity.
Yeah, there are different notions, but in one of them the C is in the target space, and the other one it is in the source space.
Yeah.
So you cannot confuse.
Yeah. If you are careful, then you are not confused. Yes. So to define this terminology, I prepare one terminology. So general terminology on conical subset. So C be a closed conical subset of vector band. So the first one is base. So this is we have already seen. So base is over X. Base is the set of points such that the fiber is not empty. So this is a conical subset. So this is the same thing as the intersection with the zero section. So this is a closed subset of X. So the second one, which we call support. So this can be confusing because this, in the case of singular support, this corresponds to support of F. So this can be a little confusing, but I don't know other words. So let me call this support. So support is the set of points such that the fiber is not a subset of 0. So we have this inclusion, and this is the image of projectivization. PC by this projection. So we can define projectivization with this conical subset in the projectivization with this vector bundle. And of course, this is projective, so this is also closed subset of X. And we have this inclusion. Okay, now with this, I can define transversality. So X smooth over K and C closed conical. Okay. So for transversality, we have morphism going to X. So this is morphism of smooth schemes over K. Then we say this H is C transversal. If the support of the intersection is empty. So here this H star C, so this is W cross XC. So in other words, this is, so we have a conical, so this is just base change, so we have a conical projection, and C is a conical subset, so we have closed, so this is just the inverse image here. So we get closed conical subset here. So this is H star C. And so this is the linear map of vector bundle. So kernel is also a closed conical subset. So the intersection is also closed conical subset. So we can talk about the support. and the condition is that this support is empty. So the support is empty means that by this definition of the support, this it says that this intersection is a subset of the zero section. So this means this is a subset of zero section. Okay, so this is the definition of the first one.
If H is smooth,
yes.
Is it always C transversal?
Well, what is it?
If H, the morphism H is smooth,
yes.
then it's always C transversal.
So the kernel is zero.
In the Beilinson definition, is it equivalent? You do get an equivalent notion if you restrict just to smooth H?
No.
No, you need arbitrary H. Okay, thank you.
Okay, so let me give you some example.
No, but still, the original idea, I think it was known for a while before, is that locally you take a map to a curve and you look at whether R phi is zero or not.
Yeah.
So you get some situations, some cotangent vectors which underlie, I mean, for which it is non-zero, and you want this to be the.
Yeah.
I think it was known that this gives a good. I'm not sure about the history. I think.
But then that would mean you could restrict.
Yeah, no, I
H.
think. So I think the main case is when the first is a tal and then you take map to a curve.
Right.
And then it is smooth.
Yeah.
And I think this would be enough to characterize the
singular support.
Yeah, I think that this because somehow generically for a point of singular support, somehow generically you have a situation where you have just one point and you actually capture the multiplicity also and so on. So this is strong enough to give everything.
I would have thought so, yeah.
Okay, so let me give you examples. So the first one explains the terminology. So we consider a closed immersion. Smooth overlay.
I don't know, but in characteristic zero, what I said is true in the classical case of
okay.
I'm not so sure about the. Yeah, okay. But now, of course, we know it after the theory is developed. We know probably the same thing. Actually, I didn't study this. I think that you know that when you take some sufficient generic thing, you get even the multiplicity. I mean,
No, we're not worried about the multiplicity yet. Yeah.
I'm not completely sure because in the classical case you get only Lagrangian things, and here it is not the case in the characteristic P case. So it's not. I'm not so sure. Okay, but you're
Okay, so let me give you this example. So we consider closed subscheme smooth over K. Then, so let's say let's define C to be the conormal bundle. So we have a nice smooth subscheme. So this is a vector bundle on Z. So we have we can regard this as a closed conical subset. Then so in this case H is C transversal if and only if this H is transversal to this closed immersion. Namely, so we consider Cartesian diagram. Then this is also smooth over K, and codimensions are the same. yeah, so this explains the terminology, transversality. The second example is just Dustin remarked. So if H is smooth, then H is C transversal for any C. So the next one is yeah, next one is also obvious example. So if C is a subset of the zero section, so this is zero section. The conormal boundary of the variety itself is just the zero section. So this is the notation for the zero section. Then any H is C transversal. And the last one is, so this one is also obvious remarks. So if C is a closed, if H is C transversal, and if you take anything smaller, then C prime H is also C prime transversal. Okay, so this is the examples of transversal motion. Okay, so we are completing the definition. So this transversality is done. So next I have to explain what is acyclicity. But maybe we take a little break, 5 minutes. So yeah. Okay, so yeah, we need to define this terminology. So first I need to define this, what is this H0C. So we need a small lemma. So let E to F be a linear motion of vector bundles over X and C closed conical subset and suppose the intersection the support of this intersection is empty. Then this map is finite on C. This means that if you give some closed subscheme structure on C, then the motion C to C from C to F is finite. And consequently, the image the image will be a subset of C, subset of F, but this will be is a closed subset. so I omitted the proof of this, but so you can prove this using graded ring. So, of course, the assertion is local, so we can work locally. So everything with graded ring. So the most here can be regarded as most of graded rings. And the closed conical subset is defined by graded ideas. So here we use the assumption that this is conical. So conical means that this is stable under the GM action. So stable under the GM action means that this is defined by graded ideal. And so the conclusion is this quotient is finite over A, and the assumption here is that B divided by J plus. So this is graded ring. So the the element of positive degrees forms ideal. So this is finite over. So you can interpret this assumption like this, and you want to show this implication, and this is some exercise in commutative algebra. So I will leave this to you. Okay, so we apply this to this situation. So, yeah. So for us, this is the pullback of tangent band, cotangent band. So we apply this to this mechanism, and C to H star. Like this. And the transversality was this condition. The intersection of kernel and this pullback is subset of the section. That was the condition. And then we have this conclusion. So so this one, H of C, is the image of this pullback by this map. By this map. So this is a subset of T star W, and this is a closed conical subset. So this is the definition of this H naught of C. Now I go to this acyclicity.
So when H is a tall in particular, nothing is happening.
Nothing happens.
H0 is H star.
Yeah.
Okay.
Okay. Okay, so definition. So F is morphism of smooth schemes over K, and C is a closed conical subset. Then we say this F is C-acyclic if the support of the inverse image of C by this map is empty. So we have map from X to Y. So on the definition form, you can pull back definition of Y to definition of X. And C is a closed conical subset. So you can define the inverse image as a closed conical subset here. And the condition is that the support is empty. So that means that the inverse image is a subset of the zero section. So this is the definition. So let me give you examples.
So in particular this,
Yes.
Yeah, this is very, yeah, so this almost implies that F is smooth, because
Yeah. Yes.
if C is non-empty, then F must be smooth in the neighborhood of the,
Yes, yes.
okay.
Yes. Yeah. The first one. So if C is a subset of the zero section, and if F is smooth, so if F is smooth, this is just an injection, and if C is a subset of zero section, then F is C-acyclic. And second, if second one is, so X to spec K. So this is C-acyclic. For any C. Next one is if X to Y is C-acyclic, and Y to Z is smooth, then X to Z is C-acyclic. And if F is identity, so identity is C-acyclic if and only if C is if C is a subset of the other section. Yeah, and the last one is, so I will write later. So this is exactly what Gaba said. Okay, so So we have this examples, but this example up to 4 correspond exactly to example 1.2. So this is correspond to local acyclicity. So yeah, so this condition correspond. We will see later that this correspond to that corresponding F is locally acyclic and F is smooth. Then this most is locally acyclic. So this is smooth local acyclicity or smooth motion. And if the target is spec K, so everything is C acyclic. So yeah, so this will correspond to generic local acyclicity. And next one, so next one is about the generalization of this. But so we had some property like this in for F acyclicity. And the identity for the sheaf case, identity is F acyclic if and only if F is locally constant. So this is also correspond. The last one is the last one is if F is C acyclic, then F is smooth on the neighborhood of the base of C. Okay. Now this definition is completed. So now we know what micro-supported means. So yeah, micro-supported means that you should have this implication. For any such pair of motions, the first one is C transversal, and the second one is acyclic with respect to this pullback of C. Then the second motion should be locally acyclic with respect to the pullback. Yeah, and because the smooth motion is transversal, so we can put universal here. Okay, now I can give you examples of micro support. So the first one is every sheaf on X is micro supported. On this X. Yeah. I forgot to say one more thing before giving the example. So in this definition, this condition always come in this combination. So the first one is C transversal, and the second one is acyclic. So this is a little bit cumbersome. But we can say this in one word. So we can consider this pair of motions as a map from W to X cross Y. Okay. Then the combination, this combination is equivalent to this momentum is C cross T star Y vice versa. Yeah. So we always use this combination, but we can, yeah. So it simply means that so this product is a closed conical subset of. So we can identify this product as the product of cotangent band of the project band product, and under this identification, this is equivalent. So this is a simple exercise, so I will omit this. Okay, so I will tell you why this using this. Okay, so so now here we take C to be T star X. Then this momentum, and we say if this condition is satisfied, we say this pair is C acyclic. We say this condition HF is C acyclic. So in this particular case, we consider C to be this whole cotangent band. So this means that the condition, so HF is T star X acyclic. So this means that this means that the kernel is a subset of zero section. So this means this map is smooth. So the question is local, so we can assume that so we may assume so we want to check that this condition implies the local acyclicity, and the local acyclicity is a local condition. So we may assume W to be AN cross X cross Y. Because local acyclicity is zeta local. Okay. So now consider this Cartesian diagram x spec k x cross y so y cross n and w. Okay, and our sheaf is here. So we and we want to show that this is the conversion here is H, and we want to show that this conversion is H star F acyclic. Okay. So by generic local acyclicity, so this map here is universally locally acyclic by generic local acyclicity. So by this cotangent diagram, so this is H star F acyclic. And this map is of course smooth. So by example 3 in 1.2, this composition is H star F acyclic. So every sheaf is micro supported on T star over X. Yeah. Is this okay?
But you don't use really that it is AN.
I don't use what?
Okay, it doesn't matter. It says trivial.
Okay, the second example. Second example is that if F is micro supported on C, then the support of F is a subset of base of C. Okay. So this is easy. Let's check this. So let's see. Let's put U to be the complement. So we want to show that the recession is 0. Okay. Okay. So we take H to be the inclusion, and F to be most to A1, and this is just constant map 0. Like this. Okay. Then so there is no C on this U. So this is this HF is C acyclic. So just by this micro support condition, this map here is F is to U acyclic. But so we have U to A1, and everything goes to this 0, and and you check this local acyclicity. So this is S, and you can take T to be the generic point. Then on the generic fiber it's empty, so there is no, yeah, and the condition was that fxs to I star, I made a mistake here, but so this is isomorphism, and this is 0, so this must be 0, and everything must be 0. Okay, so this is the second one. So the next one, so next one is related to Gaber's comment. So assume F is micro supported on C, and suppose we have open subset, And this restriction is micro supported on C prime, so this is a subset of T star U. Then the original one is micro supported on C, restricted to the complement, and you take the union with the closure of this C prime. So you regard this as a subset of open subset of T star of X, and you take the closure to get to conical subset here, and you take the union. So if you restrict it to U, then you recover original C prime. But on the complement, you put something like this. Okay, let's prove this. So, okay. So let's call this C1. So we need to test that condition. So assume H and F is C1 acyclic. Yes. Sorry?
Is it obvious that C1 is closed?
C. Because it is a union of two closed things.
Is that what? Closed?
Yeah. What is closed?
Of course. Thank you. It was a bad question.
Okay. Okay. So we have yeah, H is always mapped from W to X and F is W to Y. So here we have U and the complement. So on U, so first we consider on the inverse image of U. This HF is just C prime C prime acyclic. So F is H star F acyclic. So it's fine on the inverse image of U. On this complement, so on the neighborhood, sorry, on the
okay, but on the neighborhood of every point on X minus U, you can use what you already know, because so it's again the same.
Yeah, on the inverse image, of a certain neighborhood of X minus U, this HF is C acyclic. So it seems that we can say this only on X minus U, but the transversality condition is that the support is empty and the support is a closed subset. So we can find such.
Maybe you have to interchange the word. Is it on the inverse image of a neighborhood or neighborhood of the inverse image, which could be smaller? Because you know just that point-wise.
Yeah. Yes. Thank you. Yeah. Yeah, on the neighborhood of the inverse image, yes. Yeah, thank you. Yeah. the transfer site is the support is empty, but support is defined as a closed subset. So we get this open condition. We can find this neighborhood. So on this neighborhood, we get if let's to say W, and W is already there. So I don't know V is H star F acyclic. But the inverse image of U and this V, the union, so they cover this W. So it's H star F acyclic everywhere. Okay, so let me give you my example. So the sheaf is 0 if and only if F is micro supported on empty set. Yeah, if is 0, then the pullback is acyclic anyway. So this implication is obvious. And the other one, we have already seen that, yeah, the second point of that one implies the opposite. And then the next one is less trivial. So F is locally constant. If and only if F is micro supported on the zero section. So this follows from the local acyclicity of smooth motion. So let's check this. So F is micro supported. So suppose HF is T zero section acyclic. Then this imposes no condition H, but on F, so that the support is everywhere. Sorry, the base is everywhere. So F must be smooth. And then F is H star acyclic. So F is smooth, and this is locally constant. So this is local acyclicity. Okay, let's check the other one. And the other implication. Yeah, okay, suppose F is micro supported on the zero section. Then we consider this pair, identity of X. Okay, so this is zero section acyclic. So the first one is smooth, so it's okay. And the second one is also smooth, so this is also okay. Okay, so this implies that the identity is F acyclic, and we have seen in some examples this implies F is locally constant. Okay, so these are elementary examples of micro support. So now we have defined micro support. What micro support means. So we know what means the singular support. So it's the smallest one on which the sheaf is micro supported. And now we want to know the existence. So the proof has 2 steps. So the first one is reduction to projective space, and the second one is of course proof for projective space. So today I have still 20 minutes. So let me try to complete the first one. So this is goes in by 3 steps. So for first reduction to affine schemes. So this is the first step. So I will make this more precise, but this is some consequence that the existence of singular support is a local property. And the next one is reduction to AN. So any affine scheme is a closed subscheme of affine scheme. So here we need to study closed immersion. And then reduction to PN. So affine scheme is an open subscheme. AN is an open subset of PN. So here again we need to study local property. Okay, so let me start with the local property. So it's the following proposition. Okay, the first one is let U be an open subset. Yeah, X is smooth, okay. So if F is micro supported on C, then resultant to U is micro supported on C resultant to U. And if further if this C is a singular support, then the singular support of the recession is the recession of C. This is the first part. So this will be enough for the last one. So if you apply this X to X equal Pn and U equal An, then if you know the existence of singular support for Pn, then you know the existence for An. And next one is for open covering. So CV are called conical subset. So if so the extensions are Markov supported on restrictions for every I. Then F is Markov supported on C. And further, if this CUI are singular support of restrictions, so if this is satisfied by the first one, the patching condition is satisfied. Yeah. So it's not. Yeah. So sorry. Yeah. So yeah.
If the singular support of the UI exists, then you can say that they patch to the singular support of F.
Yeah. So this was not the good way. Yeah. So C must be just in the previous sentence. Yeah. Yeah. If CI is yeah, and then the union satisfies restriction is CI, and C is the singular support. Sorry. Yeah, if you know the existence of singular support locally, then by the first one, we have the patching property. So we have globally well-defined closed conical subset, and this global one satisfies the singular support. Okay. Yeah. So the proof of this is rather elementary, except this one. Yeah, otherwise nothing special happening. So let me prove this one. Okay, so we want to suppose we already know this. Okay, and suppose we know that C is a singular support, then the restriction is also singular support. Okay, so we want to show. Yeah, so we need to show the two things. So suppose we know C is singular support. So we want to show that F restricted U is co-supported on the restriction. So this is the first thing. And we have to show that this is the smallest one. So if restriction is micro supported on C prime, and then C prime must be larger than this restriction. So this is the definition of singular support. So we have to check these two conditions. And this first one is exactly this. So we skip this. So we need to prove this. Yeah, I think this was just erased here. So so by this condition, our F is micro supported on this C. And the restriction is micro supported on C prime. So this implies that F is micro supported on the union of C raised to the complement and C prime closure. Okay, like this. So F is micro supported on C, and on U it's micro supported on C prime. So this implies that F is micro supported on this union. So we have seen this in this example. Now we use the fact that this is the assumption that this is singular support. So this is smallest, so we have this inclusion. And then we can take the restriction to C to U. Then we recover C prime from the left hand side, and on the right hand side we get this. And so this is what we want. Okay, so yeah, so this is local property of singular support. So I skipped some elementary fact, but it gives this reaction to that reaction. So now I go to this closed immersion. Yeah, closed immersion. So let I x to p be a closed immersion of smooth skins over K. So we consider such situation in general. And C is the following construction. So C will be a closed conical subset. So then we define I naught of C as a closed conical subset of T star of P. And in fact, this is a subset of T star of P restricted to X. So X is regarded as a closed subset of P. And then here we have surjection. So if you have a differential form on P, then you can regard it as take a restriction to X. So we have this surjection, and here so we have this C. So we can take the inverse image here, and we can regard this ideal C as a subset of T star P. So this is the construction. So next Monday, this construction will be more general to proper more smooth. So but here I only use this for closed immersion. Okay, so so I can give some example. So if C is just the zero section, then this direct image is nothing but the conformal boundary. And more generally, if C is, if we start from general conical subset, and if H W P is transversal with respect to this push forward, then our H is transversal to the immersion, to this immersion on the neighborhood of C. Yeah. And further, so we can consider Cartesian diagram. So this condition implies that this is smooth over K on the neighborhood of the inverse image of C. And here, so after shrinking, we can regard as a smooth subscheme. And then, so let's call this H prime. And this H prime.
What do you mean a neighborhood of C?
Sorry?
It's called H. Because
yeah.
you need to give a subset of the source. I mean, H is count from W to P.
H is W to P, yes.
Okay,
and C is here. And I is here.
Yeah, but to say on a neighborhood.
The inverse image of, sorry, the base of C. Thank you. Is it okay?
Okay, so you have to erase what you want on the neighborhood of C there.
Yeah, here also, yes. It's okay?
The base of C is a subset of
base of C. C is conical subset here, so base is a closed subset here.
Okay.
Yeah. Okay. So this is smooth on the inverse image of this base. And so the transversality is anyway only related to this C. So this H prime is so maybe so to let's say neighborhood of V prime. H prime related to V prime is C transversal. Okay. Yeah. So yes. So so we have a similar proposition for closed immersion using this construction. But I will continue next week. Yeah, thank you for attention.